Okay, well, we finally made it out of Chapter 1, and now we are ready to begin Chapter 2, which is way more exciting, if in my personal opinion. Chapter 2 is all about derivatives, okay? So if you don't know what that is yet, this little video is going to help you try to start to figure that out. This is just a little PowerPoint that usually I have you guys go through together, but since we're doing this via a video, I'm going to just kind of scroll through here, okay? So the first question is, what is a derivative, right? And intuitively, we say the derivative measures the rate of change of a situation. So you guys have been very limited to this point. Measuring rate of change, you've really only measured it for like straight lines, right? Slope is how you calculated the rate of change of items in the past. But we're going to extrapolate this and make it more robust, and we're going to consider functions, which again, you can see where these boxes are. There used to be a fancy-looking function here. All you need to know about this function is not linear, okay? So we have a very complex function here, and it models the population of a bacteria as time goes on, right? So the derivative would measure the rate of change of that bacteria throughout that population. So last year when we went over this, right, Ebola was a big topic and how fast that spread. So when we talk about what types of careers might be focused on figuring out how fast bacteria's populations spread, right, at different times, 2 hours, 24 hours, 5 days, right? People that kind of, make vaccines, right? World Health Organization, the CDC, people that are interested in going into medical careers, the rate that those, diseases like move through a population is actually pretty interesting stuff, and they need to know that. So a derivative kind of, what we're starting in Chapter 2 is a baseline for all of that. Okay, here's a business tie-in. Let's assume a company has decided they're not going to advertise in print media, so no more newspapers, right? And they're only going to go online, okay? They have found a function that models their units of sales with respect to time since the switch, okay? And again, a nonlinear function is here, and the question is, why might they be interested in monitoring the rate that their sales are changing? Well, they want to know, was that a good call? Are there certain markets where we should still be advertising in the media, in the print media? Are there certain places where we shouldn't? Are these websites that we've chosen to advertise on working? Are they not? Okay, so the rates that things change throughout business and real estate and gobs and gobs of tie-ins is a pretty important task that business have to figure out. This is just a nice picture I stole from your book. I'm trying to see if I can make it be without the glare here. So this is exactly what I was stating before. Previously to today, you've only been able to calculate the slope of a line, right? Change in y over the change in x, okay? If you had a curve, right, the best you could do is pick 2 points and draw a secant through that line, or a secant through that curve and calculate the slope between those 2 points, right? Well, now what we're saying, now that you have calculus in your life, we can pick the slope right here at this point on this function, right? Or up here, we can pick the slope right there and know what it is, okay? These are done by figuring out the tangent line to the curve. And you notice how the tangent line only goes through one single point, right? Well, calculus is what allows us to find the slope of this blue line. Previous to today, you've always had to have 2 points to determine the slope, okay? So in the most basic sense, the derivative is the slope of the tangent line. That's what you need to commit to memory. However, that's not the actual definition of the derivative. I'll give you that definition in a minute. Okay, but let's talk about this tangent line and why it's interesting. Well, tangent lines sometimes have slope of 0, sometimes they have negative slope, sometimes they have positive slopes, okay? And a lot of times what happens at this peak, right, the slope of that tangent line happens to be what value? What do you think, right? Right, it's a horizontal tangent line, so the slope is 0 there. And again, a lot of times in modeling and businesses and forecasting for whatever company you're working for, they're interested in knowing, when do these peaks happen? When am I selling the most iPods, right? When is conversely, right, when do the valleys, when do those happen, right? And these tangent lines are indicators that something is peaking or on the opposite end of the spectrum kind of bottoming out. So it really is an important business concept, okay? So more importantly, we can utilize information from the derivative to make predictions about a function's max or min. So that's the places where the tangent line is 0. Okay, there's one about infrastructure, right? So if you're thinking about being a civil engineer, a company has put together, right, this flow rate. They've come up with a model for the flow rate on, let's say, the interstate or something, and they're trying to figure out how can I divert traffic or change the roadways to kind of alleviate this congestion, right? Well, they're trying to figure out, right, I need to maximize the speed of the cars, right? So looking at these models and for places where they have those peaks and valleys, is really going to help them maybe make judgment calls about their engineering plans. So I just want to pick a couple examples to kind of point out that, you always say, oh, when are we ever going to use this? But the reality is lots of analysts can use the information, right, that you've been given. Okay, so that's kind of like the big picture thinking of it. Now today, of course, you're supposed to learn the actual definition of the derivative. Okay, so if you want to get your notes out, right, you're going to start copying here. It's going to be a long video, sorry for that. Okay, so I said intuitively we think of it as the slope of the tangent line. Okay, so that's the first thing we want to note. A derivative is simply the slope of a tangent line. Okay? That is not the actual definition. Okay? The actual definition, when I ask you to memorize this, of the derivative is given by a limit. So it's the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay? And now you're probably like, what? Okay? This limit doesn't make a whole lot of sense right now, but we're going to try to unpack it and see if we can get it to make sense. So to do this quickly, let's start off with just a grid here. Okay? And I'm going to pick a function, just a random looking function, let's call it like this. I'm going to pick a random point. So here's a curvy spot on this line, right, on this function. Okay, so this guy is f of x. And I want to know, like, what is the slope right here at this specific point, right? So if I had a straight edge, this is all I got here, I'm going to draw this tangent line. See how close this gets to looking tangent. Pretty close, right? So this is the tangent line. And of course, I want to know the slope of this line specifically. Well, I don't have 2 points, right? So what we're actually going to do is we're going to use the secant line to be the, as an aid to help us get the slope of the tangent line. So let's see if this pen will work. All right. So let's say I pick a second point on this function right here. Okay. We're going to call the original point that we wanted the slope at, we're going to call that x. And what we're going to do is we're going to call the x value of this point x plus h. Okay. And we're going to assume that the distance between these 2 points is represented by that letter h, right? And so that's why it makes sense to call this x. This distance is h, yielding x plus h right here. Right? And so now think about the tangent line, right? Or the secant line, sorry. Okay, and this guy's slope. Okay, so let's call this the secant line. Okay, now I definitely know how to figure out the slope of that secant line, right? I simply take the change in y, right, divided by the change in x. So if we're using function notation here, that means that the y value associated with x over here is going to be f of x. Okay, and of course the y value associated with this x plus h here is going to be f of x plus h, like that. Okay, so all I'm going to do is I'm going to figure out the slope between these 2 points. Okay, and so that would be, right, the change in y's, if I subtract the y's, f of x plus h minus f of x, that's the notation that we kind of start to see up above, right? And then I need to divide that, right, by x plus h minus x, right? X plus h minus x. That's the change in x. Okay? So this is much like what you've done in the past. Okay? So I end up with this expression. Of course, down here the x's cancel, and all I have left is h. Well, what the geniuses did back in the day, right? Whoever discovered the derivative, maybe Leibniz, we can look that up, tell you more about him later, is they decided, well, hey, why don't I take this point and move it on a course this way, right? instead of this secant line, that's not very helpful to coming up with the slope of the pink line, right? Why don't I move this point over here? And now imagine this secant line slope here. Which one is closer to the pink line slope, right? Well, obviously the dotted line. Well, then they said, okay, well, why don't we move that even closer, huh? And then they started thinking about these secant lines, right? Getting pretty darn close to what the pink line slope is. As you move this point closer and closer, i.e., you let this h value become next to nothing, right? You let the limit of h approach 0, right, of that expression. And that's what gives you the derivative, okay, the slope of the tangent line, okay? So what we call this, some new notation for you, is f prime of x, okay? This is what we call Lagrange notation, I think. So f prime of x, it's just an apostrophe to represent the derivative, right, of the function x, okay? So this is the derivative of f of x, okay? This is how we calculate it. Okay, so this is a really big concept right here, okay? This spits out the derivative, okay? And so what I'm going to do is have you guys, if there's just 2 examples maybe I could do with you today, I just want you to repeat those problems again and again tonight for homework, okay? And so let's start off with example 1, okay? So let's use this derivative, right? And come up with, let's do a tangent line. Okay? So find the equation of the tangent line of the function I'm going to give you is x squared plus 1. And then the x value I want that tangent line at is x equals 1. Okay, so if I give you a picture, right, of what's going on here, let's assume that we have this function, right? We can all draw x squared plus 1, right? It's a parabola moved up 1 unit. Okay, and the tangent line at 1 specifically, right, is going to be at, let's say, 1, comma 1. Okay, well, that's not good. Let's say this is 1, comma 1. Okay, and I want to know the equation of this line. This is the tangent line there. So I have to go after and figure out its slope, okay? I also, of course, know that if I plug 1 into this function, right? Oh, that's right, 1, comma 2, right? I get 1, comma 2 out, okay? So I know that the point that this goes through right here is 1, comma 2. The question I have is what's the slope, okay? So here's how we calculate that. We're going to take the limit as h approaches 0. And we are going to use the limit definition. So I'll write that again here. So this is our model. Okay, but now we're using this function to rewrite this expression so that we can solve for it. So the limit as h approaches 0, I have to plug x plus h into this function, right? That's what this first statement says to do. So I'm going to have x plus h squared, right, x squared, and then plus 1. So that is this part right here, okay? Then it says to subtract, minus, we're going to subtract f of x. So since it's a sum, I'm going to subtract it in parentheses, and I just put f of x after the minus sign, okay? And then I go ahead and try to work this out. Okay, if I put 0 in right away, it's important to note that I do get an indeterminate form. So we're going to have to manipulate this a little bit and try to get this h to cancel so that I can actually figure out what my derivative is. Okay, so remember this is our derivative f prime. Okay, so I'm going to go ahead and I'm actually going to square this out. So make sure that you FOIL that, right? When you FOIL that, you get x squared plus 2xh plus h squared plus 1, and then I'm going to apply my subtractions here. Of this, okay, all over h. And now you should see some good things starting to happen, right? I should be able to take this expression here and cancel things out, right? For example, the x squareds cancel, right? The plus 1 and the minus 1 cancel. And the expressions that remain each have an h in them, so that's good news because now I can take out one h from all of these, right? And so I can, to make it look prettiest, I'm going to factor out an h from the numerator and leave that all over my h so that you can see those h's cancel. And what I have left to take is the limit as h approaches 0 of 2x plus h. So that's all that remains. So I'm going to put 0 in for h here, and I get 2x as my answer. Okay, and that must mean that this is a derivative. Okay, so when we talk about this function 2x, right, this is considered a slope generator. Okay, and this particular function 2x will tell me the slope on this parabola at any point that I'm at. So if I want to know the slope at 1, I just have to plug in 1 here. So f prime of 1 is how we show that. That's equal to 2 times 1. So my slope is 2. Okay? So the question, original question, said find the equation of the tangent line, right? So I know that it goes through 1, 2. I'm going to use point slope form. So using the point 1, 2 with slope that I generated of 2, I get this equation. Y minus 2 equals my slope times x minus 1. Okay? Okay, now here's another thing. If I wanted the tangent line at x equals negative 3, right? Well, that means I'd be back on my parabola. At negative 3, right, my y value is how much? Well, I got to figure that out by plugging it into my function. So f of negative 3 is basically 9 plus 1, or 10, right? So I know this is the point, negative 3, comma 10. Okay? And so I can take that information, since it goes through the point negative 3, comma 10, the next thing I would need is my slope, right? My m in this case, I would get by plugging the x value into my slope generator, or my derivative, right? So 2 times negative 3 would be negative 6. And so now here's my new equation, y minus 10 in point slope form. It's always the easiest. Okay, you never want to go diverge from it. Okay, this would be the tangent line equation at negative 3. I have a new point that it goes through and a different slope because I'm on a different part of the parabola, right? Isn't this slope obviously negative, whereas this slope was obviously positive, and that kind of came through in my tangent line equations. Okay, so let's try one more so that you can kind of get practice with this tangent line with the slope, sorry, with the derivative formula. Let's just do a simpler one. Find the equation of, this is example 2, of the tan line at, let's do x equals 5. If f of x equals, what would be fabulous? Let's do, I don't know, 2x minus 3. Okay? So I have the x value. This is a linear function. It's kind of a hint there. Let's use the limit definition to come up with the derivative. So I'm going to do this. Remember, I have to do f of x plus h. So into this x, I'm going to plug in x plus h. So my first statement is 2 times x plus h minus 3 minus, now I do f of x according to my definition, right? Which in parentheses is 2x minus 3. And that's all over h. Okay, so this looks much like last time. Okay, you'll notice if I put in 0 for h, I get indeterminate answer, 0 divided by 0. So I'm going to try to finagle this a little bit, right? And I'm actually going to distribute this through and see if I can get these h's to eventually cancel. Okay, so I have 2x plus 2h minus 3 minus 2x plus 3 all over h. Turns out, right, that these 2x's cancel. This minus 3 and this plus 3 cancel. And this is the expression that I'm left with. So indeed, even my h's will cancel. So I'm left with limit as h approaches 0, really of the number 2. And we know that there's no h to play a role here, so my answer is 2. Okay? So this is a linear function, so it's not very exciting. But let's use this slope. So I've got y equal to 2 times x minus 5. And then, of course, if I plug in 5 to this function, I get 10 minus 3, which is 7. So f of 5 is 7. And that's how I know what to put here. And really, this is the equation of this line, right, in another form. Because if you think about the equation of 2x minus 3, this is the original f of x, right? Well, I was asking you for the slope at x equals 5. Let's say 5 is here, 7's here, okay? Well, the slope of this line right here, of course, is going to be 2 because it's the tangent line would happen to lie right on top of the function f of x, okay? But I just wanted to at least show you another example of this limit definition in use, okay?